talk about a subject which I had almost forgotten about yesterday, so I tried to get myself informed, and I hope this will go well today. So what I want to present is a proof of the ergodic theorem. Okay, and this is what will help us to prove the law of large number for the random walk in random environment under the average measure. Okay, so I'm not sure about. Okay, I mean, it has to come from Russian, so perhaps I don't have to worry about the spelling. This is due to Birkhoff and von Neumann. Okay, I will tell you later why there are two authors. This is from the 30s, 31, 32. Okay, and it's basically an extension of the law of large number. And somehow, yeah, I also discovered yesterday that yeah, the proof of this theorem is actually the proof I give for the law of large number in L1. So it's also perhaps, okay, the proof I will show you, it's not the original proof, but it's perhaps one of the shortest proofs you have for the law of large number. Okay, so okay, before stating the ergodic theorem, and I will state a restricted version which will be more than sufficient for our purpose. Let me introduce some notion about measured dynamical systems. Okay, so we consider omega f mu a probability space. And t from omega to omega a measurable transformation. Okay, so definition one. We say that the transformation T is measure preserving if it preserves the measure mu. So if the image measure of mu by T is equal to mu. If T star mu is equal to mu, okay, where we call that T star mu of A, okay, it's I don't remember. I think it's the push forward of the measure mu. I don't remember which size is push and which size is pull, but it's I think the push forward of the measure mu. So this is equal to mu of the pre-image of A. Okay, where T minus 1 of A, well, it's the set of omega in omega. Such that T omega belongs to A. Okay, so basically what this tells you is that, well, if you take a variable x with value in omega and distribution mu, and you look at T of x, well, then this has also distribution mu. Okay, and yeah, just not a big spoiler, but when I will apply the theorem, somehow this omega will not be the random environment. Okay, so just okay. So what are examples of this? Well, OK, I will give you the examples we are interested in, but I think first I should give you the simplest examples there are. So first one is omega is equal to R over Z. Mu is the uniform measure, also called the R measure. OK, so just, I mean, this is just the interval 0, 1, right? So just the uniform measure on 0, 1. This is 0, 1, but considered as the real number modulo 1. OK, and T alpha of x is equal to x plus alpha, where alpha belongs to alpha over z is fixed. OK, so this is just rotation on a circle. OK, you just rotate by an angle which is, well, if you want, 2 pi alpha. OK, so this is A. B is the doubling of the angle, so same. OK, so well, you see, this thing is bijective. This thing is not. OK, but you don't need to be bijective to be measure preserved. OK, and I think it's a simple exercise to show that these things are measure preserving. In fact, this is almost a definition of Lebesgue measure. And yeah, this is little more than, OK, this is a simple application. OK, so the second thing is, well, omega is equal to x to the n, or x to the z. And nu is a probability on x. OK, x is just measurable space. OK, and mu is equal to nu or nu to the power z. OK, just product measures, infinite product measures. OK, so what this means is that omega is equal to omega x, x belongs to z. And this thing, if omega is distributed according to mu, well, these things are IID and distributed according to mu. OK, and what is the T I want to talk to you about? Well, you can take anyone, x, z. OK, let's say from omega to omega, because and T omega is equal to omega x plus 1 x in z, or omega x plus 1 x in n. So what you're doing is you're shifting all the indices by 1. OK, and yeah, in the first case, OK, for in this, I don't know, the second case or first case, you have a bijective transformation. OK, the inverse is just the shift by -1. Here, when you're shifting, you're basically losing the first coordinate. OK, and OK, fun fact. Well, okay, 1b is equal to 2. So if you take the doubling of the angle, this thing, it's a shift operation. Take, okay, x being equal to 0, 1. Okay, and then you have a bijection between the two omegas n. Consider the dyadic development of x in. Okay, so if you identify x with its dyadic development, well, it's an element of 0, 1 to the n. Okay? And what you're doing when you multiply by 2 is you shift every number of the dyadic development. So you're just performing this operation. Okay, so I just gave you 2 examples in the end. Okay. So now comes a second definition, which will be the important one. So, okay, in fact, the 2 definitions are important. We say that T is ergodic if T minus 1 of A equal A implies that mu of A is either 0 or 1. Okay, so if an event, or if a set, if a measurable set is preserved by T, okay, in the sense that its free image is equal to itself, then it has to be trivial. Okay, and let me give you examples. So T alpha is ergodic if and only if alpha doesn't belong to cube divided by z. Okay, well, okay, one direction is quite simple, like this thing, because if alpha belongs to Q, your transformation is periodic. Okay, and you just have to take, well, you will find some segment. Well, I mean, basically, yeah, if it's periodic, it means that any A will be invariant by T to some power. So you will find a contradiction to that. Okay, if alpha is irrational, well, somehow it has to do with the fact that the orbits of these transformations are dense. Okay, and you can use this information to show that the system is ergodic. Okay, by the orbits, I just mean, well, you take x, you take the iteration of t, and this gives you a sequence. This sequence is called the orbit of x for this dynamical system. Okay, so easy and okay. Okay, and all the rest is ergodic. So. 2 are ergodic. Okay, and yeah, I think I'm including a proof of this. Let's see. My notes are not in the right order. So. Yeah, it's not very difficult, but okay, I'm not giving a proof for 1b because 1b is the same as 2. So let me include a proof, and yeah, it's the same proof in the two cases. So let me consider the case of sequences indexed by the natural integers. Okay. All good with the definitions? Okay. Okay, so the idea of the proof is quite simple, and it can be used in other contexts. So the idea is that, okay, let's assume that you have an event which is translation invariant. Okay, this is what this means. Then what you can do is you can approximate this event by a cylinder event. Okay, so an event that depends on finitely many coordinates. Okay, and you won't change the probability by much. Then you can show that this event is well approximated by its translation. Okay. Now, these things gives you that, okay, for this event, for this modified event, these things are not equal, but they are almost equal, like, because both sides are well approximated. Okay, and now this thing, if you translate them far enough, they are independent. So then you're done. Okay, so this is the idea, and what we want. Okay, proof. We want to show that A equal T minus 1 of A implies that mu of A. Okay, but I will just write P because I'm much more used to P. Okay, so in this context, P of A is smaller than P of A square. Okay, and if you do this, if you have this, you're done. Okay, because this thing can be true only if P of A is equal to 1 or 0. Okay, so yes, so okay, we can find AN, and so AN belongs to sigma of x1 xn. So here I'm using the notation that xn of omega is equal to omega n. Okay, so this xn is the random variable which is given by the nth coordinate. And epsilon n going to 0 such that P of such that A is a good approximation. AN is a good approximation of A asymptotically. Okay, we don't have anything quantitative about the rate. Okay, but okay. So in particular, I mean, this thing implies that P of A minus P of AN. This thing is smaller than epsilon. Okay, again, yeah, these things are things that come from the basic probability class. Okay, when you construct product measures, you know that infinite product measures, you can prove that yeah, all events, all measurable events can be well approximated by cylinder events. Okay, so now what can you say about PA? Well, it's equal to this for any k. Okay, this is just because this thing is equal to it. And you have translation in brackets. Okay, so now what I'm saying is that, well, I can just replace this by an. Replace also this by an. And then I have to add some error term. And basically, okay. Okay, so this is just from the fact that this event here is included in the union of these three things. Okay, if something is in this intersection but not in that one, well, it's because it's either in this symmetric difference or in this symmetric difference. Yeah, in fact, I don't, okay, yeah, it's not an intersection. In fact, okay, here I would only really need perhaps a minus an, okay, but this is true. And here also t minus a. Okay. So now I have three terms, 1, 2, and 3. So one is equal to PAN P G minus K AN if K is larger than N. Okay, if I'm shifting by K, basically this event depends on x1, xn, and this event depends on, well, xn plus 1, x2n. If I take K, well, let's say K equals to 1. Okay. Okay, so I will take K equal to 1, the remainder. Okay, 2 is smaller. Okay, and okay, so K2n. And this is okay, smaller than P of A plus epsilon n times P of T minus K A plus epsilon n. Well, okay. But okay. Yeah, okay. It's equal to P of AN square just by measure preservation, okay? And this is smaller than P of A plus epsilon n square. Okay? 2 is smaller than epsilon n. And 3, well, it's equal to 2. Well, 3, it's equal to P t minus k of AK. Okay? So you have to always to check that what you're saying is right, but it is true that the push forwards and the symmetric difference, they commute. I mean, basically, the push forward, it commutes with every operation you can do on sets. So this is the reason why it's a nice operation compared to the other one. Okay. So this gives you what? Yeah, and then you use this is smaller than epsilon. Okay, here you just use the fact that T preserves measure. Okay, so overall what you get is that PA is smaller than PA plus epsilon n square plus 2 epsilon n. And you take n to infinity and you get what you want. Okay, so now let me give you some equivalent characterization of ergodicity. So I think the definition is still there. Let me give you some alternative definitions that may seem stronger, but they are equivalent. Lemma. If T is ergodic, okay. Okay, so yes, if T is ergodic, I mean for some probability space omega f mu, then okay, I'm just writing in this form because the other implication is straightforward. So the first one is, okay, you don't really need to require this. You only need to show that this is true almost surely. Okay, so I think this is okay to say this is true almost surely. This is not really okay to write it. You have to so let me. For what do I mean when I say this is true almost surely? I just mean that well, these sets coincide up to some error of measure 0. And now let me go back to mu. Okay, so if this is true, then mu a is in 0, 1. Okay, so this is slightly stronger than this because what you require here is a bit weaker. Okay, and the second thing is for all f omega to r are measurable f of omega is equal to f t omega almost surely, well, mu almost surely. This implies that there exists C. Okay, sorry. Yeah, I think I want R union plus minus infinity. Such that well, okay, mu of f equals C is equal to 1. Okay, the set of omegas such that f omega is equal to C as measure 1. Okay, so any function which is invariant by t, which is almost surely invariant by t, is almost surely constant. And by the way, I mean, things go only one way, right? Here, I relaxed a bit this assumption, not having an inequality, but having some kind of almost sure equality. It does not mean that here you could replace this by A equals the empty set or omega. Okay, if you do this, okay, you come with another definition, and it's not an interesting definition. So, for instance, if you come with this definition, then irrational rotations of the circle are not ergodic. So. Okay. And the shift operators also. So, okay. So let me prove this. Any question on the statement? Okay, what we are going. Okay, we are not going really to use this. The important thing is just about the functional that. Functionals that are invariant by t, they are almost surely constant. Okay, so how does this work? Well, basically, from A, I want to find some A bar that satisfies this. Okay. And then, well, because T is ergodic, I know that A bar has probability 0 and 1. So I want to find A bar that satisfies this. And that is a good approximation of A. That is an approximation of A up to measure 0. Okay, so I think you have several options. 2 options are taking either lim sup or lim inf of A. Okay, so take A bar. Okay, so let's take the lim sup. So I just want to take the set of elements of A that are in infinitely many t minus k of A. So I want to take the intersect that are. Oh, let's take the lim inf. Sorry. I want them to be in all t minus k of A from a certain rank. Okay? And you can check, like if I just take the intersection, things wouldn't work. So, but basically, I'm considering here a property about the sequence, which is translation invariance. So this is what will make things work. So intersection for t larger than n, t minus k A, and then the union from n larger than 1. Okay, so what we have is that Okay, the first thing is that t minus 1 of A is equal to A. Okay, this is just because, well, t minus 1 of, so t minus 1 of A bar is equal to A bar. This is just because t minus 1 of A bar, well, t minus k plus 1 of A. Okay, so I can rewrite this as well, I can put a plus 1 here. Okay, and then I get the minus k here. Okay, and the plus 1 here, I can remove it just by, well, this plus 1 here, I can put it there. Okay, but now this union is an increasing union, so starting from 1 or 2 doesn't change anything. So here I didn't use my assumption, so I will need to use my assumption when I show that the probability of the symmetric, the measure of the symmetric difference is 0. Okay, so okay, let me. Perhaps I won't put all the detail there, but yeah, you can use a union bound. So this A bar, the symmetric difference between A bar and A. Okay, basically you know that the symmetric difference of, well, basically, yeah, you can distribute union and intersection over symmetric differences. So overall, yeah, like if I put an intersection here, basically, I know that, let me write this. I know that this or this is included in B A union C A. Okay, whatever operation I put there, if I put a union here, I'm good. Okay. So now this tells me that, well, this is included in, well, the union of k larger than 1 of mu A and k. Let's see. No, okay. Okay, let me, okay. First, it's, I want to write things like this. Let me be safe. I'm sure I'm being over careful here, so. But for sure this is true, and this is not AK, this is T minus K. Okay, and now I think this has to be true. Okay, so therefore this thing here, it is smaller than the sum from I equal 1 to k minus 1 mu t minus I a delta t minus I plus 1. No, I want perhaps 0 from k minus 1. Okay, and all of these terms are equal to 0 just by invariance by t. Okay, you're just composing by t to the minus. Well, you have t minus I on both sides. You can factorize it. Okay, and once we have proved these two things, we are done because, well, from 1 and the fact that t is ergodic, we know that a bar has probability 0 or 1. And from 2, we know that a and a bar have the same probability. Okay, so this is not something we will use. It's just about your curiosity. This is the optimal definition. Okay, you don't gain anything by relaxing a bit this assumption because you get exactly the same definition. Okay. I'm using that t is ergodic here. I'm using it here. I'm not using it in the first point, right? This is, okay, for 1, yeah. Okay, this is always, and this is if t is ergodic. Okay, and yeah, when t is ergodic means t is ergodic for this probability space. Okay, it's not ergodic by itself. Okay, it's really the full system which is ergodic. Like what's ergodic? It's omega f mu p, omega f mu t, which is a measured dynamical system. Okay, so yeah, let's move on. Any more questions? Okay, so now let's go to the second part. Okay, and perhaps somebody would have an idea of how you prove this. Okay, so I think what helps you a lot, I think this is true with some other assumption, but we will use this for the proof. So, okay, what does it mean? What do we want to prove for this to be true? What we are going to prove is that, so this is for B, we prove that the probability mu of f omega smaller than u belongs to 0, 1 for every u in R, okay, plus minus infinity. Okay, I don't, well, for plus infinity it's trivial, but not for minus infinity. So. Okay, so so if this is true, then this variable has a trivial. I mean, it means that it's let's see, what's it called? Accumulation distribution function, accumulated distribution function is a step function, so this means that this is constant. Okay, so then C will just be the infimum of the u's such that nu f omega smaller than nu is equal to 1. Okay, and how do we prove this? Well, we have the event in the set of omega such that omega nu satisfies mu of AU t minus 1 AU is equal to 0. Okay, this is this set here, it's exactly the set f omega smaller than u and f t omega larger than u union f omega larger than u and f t omega smaller than u. Okay, so because these things coincide almost surely, both these things have measure 0, so this thing has measure 0. And because T is ergodic, 1 is true, so that here we get that mu of AU belongs to 0, 1 from ergodicity, which implies 1. Okay, so now I'm ready to, okay, perhaps something that might have confused you. When I say ergodic, automatically I mean that it's measure preserving. Okay, okay, let me state the ergodic theorem in this simplified version. So somehow, if you want the more general ergodic theorem, you don't assume that your transformation is ergodic. You just assume that it's measure preserving. And also, but I don't know why you would want to do that, but you don't assume that mu is a probability. Okay, yeah, assuming that something is not a probability, I think it's, but perhaps it has application. Okay. Okay, so okay, let's consider f from okay, so let's t ergodic transformation of omega f mu. Okay, and f from omega to r. Okay, well, I don't really care what you put there. And you consider either that f belongs to L1 of mu, okay, or f is non-negative. Okay, so really you're considering f not really as a function, but rather as an equivalence class of functions. Okay, modulo modification on a set of mu measure 0. Okay, and now I'm defining Sn. So, okay. I think I won't be very coherent with my notation. So Sn, it depends on f and omega, and sometimes I will only use dependence on omega, and sometimes I will always use only use dependence in f. So if I write Sn of omega, you have to think that it's Snf of omega. And if I write Snf, well, okay, then this is okay. This is just a function. So Snf of omega, well, perhaps you can guess what it is, but it's the sum from k equal 0 to n minus 1 of f t minus 1 f well, yeah, t, now there is no minus, f tk omega. Okay, so okay, so then what's the theorem? Well, you have that the limit when n goes to infinity of Sn f over n is equal to the integral of f mu almost surely and in L1 of mu. Yeah. So this is the theorem. Okay, so yeah, so we are going to prove it in for f in L1, and then I will explain how you get it for f non-negative. It's really an easy modification, and we are going to prove the almost sure convergence, and then which is what we are interested in any case, and then I will tell you about how you get the L1 convergence using uniform integrability. So any question about the theorem? Okay, so now just an observation. If you take omega is equal to r to the n, and if you take f of omega is equal to omega 1, and mu is equal to nu to the n, where, okay, either integral of omega 1 or, well, okay, u nu U is finite, or U of R plus is equal to 1. Then you get the law of large number for IID random variables. Okay, so this is observation 1. Okay, is it clear for you that this is the case? I mean, basically here, this thing here is simply omega k. So this thing is simply xk, you know, the case coordinate application. And because your coordinates are IID, this is just a sum of the first n terms, the first n coordinates. Okay, so first coordinates, and you know that your coordinates here are IID by construction. Okay, so this is one first thing. The second observation, okay, is that in general in the literature, when ergodic theorem is applied, people will say, we'll find something like the sequence of variable xn n is ergodic. Okay, hence well, the partial sums divided by n converge. Okay. And when they say that, they don't say, okay, who is omega, who is f, who is mu. Okay, so there is two ways to understand this. Okay. So I will give you an example here. Under E0 bar, the sequence UN, which is equal to tau n minus 1, UN is ergodic. Okay, this is in the end, this is what we are going to prove. So there is two ways to interpret this, and actually these two things are equivalent. So one thing you can say, this means, so two ways to interpret this. So. Okay, so the first one, A, is to say the following. So I'm considering omega is equal to, okay, yeah. Here this thing is real valued. So you can take omega equal R to the n, and nu is equal to the distribution of xn, and T is equal the shift operator. And the claim means, well, omega f mu t is ergodic. Okay, so it means that yes, the shift of operator on this sequence is an ergodic operator. Okay. And the problem is that, yeah, somehow if you told something like that, this is very difficult to prove directly. Okay, or at least this is not the simplest thing to do. So the second thing it can mean, and this is actually equivalent, is there exists omega f mu t such that f t n minus 1 omega is equal in distribution to xn. So there exists an ergodic system and a functional such that this is true. Okay, and well, in both cases, the conclusion is the same, and yeah, basically B implies A. Okay. Well, and B implies A, and A implies B, of course, because, well, you just take these choices here, and F being the first coordinate. Okay, so I think we are ready for the proof. And perhaps a last digression. So why do we have two authors here? There are, in fact, okay. So I think the proof I'm going to give you is not the one of Birkhoff, but perhaps it's closer in spirit. But there are two versions of the theorem, and the version of von Neumann is in L2. Okay, so you take yeah, your assumption is that F is in L2 here. And in the end, you get the convergence in L2. And the proof is completely different and use just, well, Hilbert analysis. Okay, and I think the story is that von Neumann was the first to have a proof of this result, send it to a journal. The head of the journal to who he sent it to was Birkhoff, and he decided that he would read the paper after he finished his proof. So this is the reason why von Neumann's version was published later, but I think both were proved about around the same time.
Neumann didn't put it in an archive?
Yeah, no. So this was yeah. So archive is useful. Okay. But yeah, it doesn't solve all problems. I think if people have bad ethics, then even archive doesn't solve it. Okay. So what's the proof? So it's usually cited as Birkhoff theorem. It's good to remember the two names because the story. Yeah. Okay. So yeah, what we are going to consider is f bar of omega, which is the lim sup when n goes to infinity of Sn f omega divided by n. Okay, and in the same way, I'm going to consider f okay, so I'm considering here that f belongs to L1 of mu. Okay, and a first observation here is that if you look at f bar, composed with t, well, it's the lim sup of Sn composed with t divided by n, and goes to infinity. And this thing, okay, you have n terms. Basically, you start with f composed with t, and you end up with f composed with tn. And all these terms they appear in Sn plus 1. Yes. This is a bit weird. All these terms, they appear in Sn plus 1, but in this term you have here you're missing the first term. Okay? Okay. I'm just using this. It's Sn of f. Sn is equal to Sn plus 1 of f minus f. Okay, this thing tends to 0. Okay, we are in L1, so this thing is equal to infinity with probability 0. So this thing goes to 0 almost surely. And this thing goes to f bar almost surely. Okay, so. Okay, so you have that this is equal to this, and therefore f bar is almost surely constant. Okay, and the same is true for well, if you take the limit. Okay, so now what we need to prove, okay, is that f bar is equal to the integral of f. Okay, it's obvious what the result is, right? So we are going to prove that f bar is smaller or equal to the integral of f d mu. Okay, and this is the right thing because by symmetry, applying, so this means applying okay, minus f is also in L1. I mean, like the assumption of the theorems are still valid, so I can just, if I prove this also for minus f, and we have that f bar is larger than integral of f d mu, and this is enough to conclude, okay, because yeah, this is larger than this is smaller than that. Okay, so up to now, everything was kind of simple. So there has to be something a bit more complicated going on at some point, and this is now. So now we are going to use a little trick to show this, and this little trick is the one you've seen in the proof I presented for the law of large number in the probability course, if you've seen my probability course. I was a bit puzzled by this trick, and now I realize that this is just a simplified, well, a particular case of the maximal ergodic lemma, okay, which is the thing I'm going to present now. Okay, so okay, so this is kind of an intermission in the proof, but okay, so we are going to use the lemma to conclude. So I'm using the same notation as before, and now how was this? 1, 2, 3. Okay, where is 5? 5 is here? Yes, 5 is here. Okay. So we are going to define f tilde. Okay, let's consider G, okay? G in L1 of mu. Okay, we're still with the same assumption as before. T is ergodic. So G is a real valued function, which is in L1 of mu. And we are defining G tilde. Well, it's the maximum, or the supremum, over n of Sn of G. Okay, not renormalized. And over n larger than 0, okay, so S0 of G is equal to 0. Okay, and well, this is also the lim sup. Well, okay, the limit when n goes to infinity of gk, with gk being the max let me write it in full. The max between 0, S1j, S2j, Sk minus 1j. All good? So, yeah, so now what's the lemma? Well, the lemma just tells us that setting E to be the event G positive, then we have the integral on E of G d mu, which is non-negative. Okay, so let's prove this, and then let's see what's so nice about it and how it can help us in our quest. Okay, so I'm going to use the following property. So let's look at Fk for k larger than 1. And let's define Ek to be the set of omega such that f k omega is positive. Okay, so the union for k larger than 1 of Ek is equal to E. Okay, sorry, and I have a G here. Okay, so yeah, if G tilde is positive, it means that Gk has to be positive at some point. So now I want to look at the value of Gk depending on whether we are on Ek or not. So, well, if we are not on Ek, then by definition, Gk is equal to 0. G tilde k is equal to 0. Okay, and if we are on Ek, well, then Gk is not equal to this. So Gk is equal to the max over the rest. In the rest, so okay, I will write the reasoning here. So if this is not true, then we have Gk is equal to max S1 G Sk minus 1 G. And this thing, it's exactly G plus max. Then I have 0. Well, then I have S1 GT and Sk minus 2 gt. Okay, if I'm taking away the last factor, basically I'm having the others. And okay, I have not exactly the sequence of s's because things have been shifted by t, so I just have to put this t here. Okay, so and this thing here is nothing more than g k minus 1 t. So here you get g plus g k minus 1 t. Okay, and we are done. So how do we conclude? Well, the integral of g on E, okay, just by dominated convergence, it's the dominated convergence theorem. This is just the limit when k goes to infinity of this. Okay, now the integral of g, well, I can rewrite it as the integral of g tilde k minus g tilde k minus 1 composed with t. Okay, now comes the next trick. So yeah, this is on EK, but on EK complement, this is equal to 0. And this is non-negative. So this is larger than the integral on omega of the same thing. Okay. Now I use, well, the fact that t is measure preserving. Okay, I have a -1 missing. So that this is gk minus gk minus 1 mu. And now gk is an increasing sequence, so this is positive, non-negative. Okay, so all of this is a bit serious. Yeah, there is something I have not said, but okay, perhaps. Fine. Okay, this g tilde is not necessarily in L1, but we never integrate this. So the important thing here is that g tilde k is in L1 for every k, and well, this is the max of L1 functions, so we don't have problems. Okay, so this is the end of the lemma, and now we are ready to prove the theorem. Everything okay so far? Okay, so we are ready to conclude the proof. Okay, I think I can do this here. So let beta be larger than f bar. Okay, let's take a constant which is larger than f bar, and we are going to show that f d mu is larger than beta. Okay, so basically, if you're larger than f bar, then you're larger. Oh, okay, no. Then you're larger than the average of f, and this is sufficient to conclude. Or perhaps I want to show the opposite. Okay, let me check my notes. Okay, no, let's see. Okay, so let's say that this is wrong. Okay, so if this is wrong, this means that there exists. You can squeeze a beta between these two. So and in that case, yes. Okay. Yes. Okay, and this is okay. So if f is larger than beta, then the integral is also larger than beta. So therefore, this has to be true. Okay. So what are we going to do? Well, let's take g, which is equal to f minus beta, okay, and apply our maximal ergodic lemma. Okay, so we have, since f bar is larger than beta, we have d tilde is equal to infinity almost surely. Okay, Sn, it grows like yeah, that's it, yeah. Okay, because you have that Sn of g, it's equivalent to f bar. Okay. Yeah. Yeah, okay, you have lim sup of Sn of g over n when n goes to infinity, which is positive. Okay, so Sn of g goes to infinity, it goes to infinity linearly, in fact. Okay, so in particular, g bar is positive almost surely. Okay, so the maximal ergodic lemma we have the integral on omega of g d mu, which is not negative. Hence, the integral of f d mu is larger than beta. Okay, so I managed to get confused, but really there was nothing to prove. We had done our whole job before. Okay, so is the proof clear? Okay, so yeah, let me tell you how you can generalize the proof. Okay, extend the result to the case of f non-negative. Well, it's not something artificial here. Our application will deal to a case where we don't know that our increments of the tau, we don't know that they are in L1, and sometimes they won't be. Okay, so if f is positive, well, just take fm is equal to the minimum between f and m. Okay. You have the limit when n goes to infinity of Sn Fm divided by n is equal to the integral of Fm d mu. Okay, so that if f does not belong to L1, we have that for all m larger than 1, the lim inf when n goes to infinity of Sn Fn divided by n is larger than Fm d mu. Okay, and yeah, this thing here goes to infinity when m goes to infinity. And here, I have no n. Okay, I'm just using the fact that this thing is larger than this thing. Okay? Okay, so yeah, in the case where f is positive, in fact, you just have to care about the case where f is non-integrable, and in that case, this thing goes to infinity. Okay, so I think we won't have the time to fully show that this thing implies our theorem, but let me try to do some part of the work. So let's try to do to give you the beginning of the construction of the system, the ergodic system for which the ergodic system to which we are going to apply the ergodic theorem in order to get our result about the expectation of tau k. Okay, and it starts with an important idea, which is which is something perhaps you have already seen in probability class. Basically, when you want to construct things in probability theory, perhaps the best things to start with is a collection of IID uniform random variable on tier 1. Okay, so our omega, the omega that we are going to consider for our problem, it will be, one part of it will be the random environment, okay? But we will also add lots of 0, 1 uniform random variables that we are going to use to construct trajectories of the random walk. Okay, and then our operator will be some kind of shift operator. So on the environment, we are going to shift. And on the other random walks, we are going to shift, but in some different way. Okay, so construction of xn, which is distributed like P0 omega from U01 IID random variable. And here I'm taking a fixed omega. Okay, so I'm going to consider psi j, j larger than 0. IID uniform random variables on 0, 1. Okay, now I have this. I want to construct, basically a sequence xn of psi with distribution P0 omega. So, okay, does anybody has an inspiration on how to do this? Okay, so what you want, basically you want to, when I mean this is, you're not allowed to use some extra randomness. This is all you have. Okay? And what you want is to make sure that, when you know xn, what's the probability to go to xn plus 1 at the next step? Well, it's independent of the past, okay? And it's a Bernoulli, but which depends on, well, xn and omega. Okay? Well, I guess all of you know how to construct a Bernoulli from a uniform, right? So this is what we are going to do. We are going to use, so we start with x0 equal to 0, and then we say that xn plus 1, it's equal to, xn plus 1 if psi n is smaller than omega xn. Okay. And -1 if psi n is larger than omega xn. Okay, so xn is really a function of the size. So now we need to check that the work constructed that way has indeed this distribution. So what do we need to check? Well, we need to check the probability of let me call, I don't know, Q, okay, the probability, the distribution of this. Okay. So now what's the probability that x0 equal x0, xn equal xn, where x here, it's the functional of psi that I've defined over there. Well, okay, first of all, this thing is equal to 0 is if things are not nearest neighbors. Okay. Yeah, what can we do? Okay, so I think what we can do here is yeah, so this is, okay, this is Q. Okay, here when I'm given this, I'm given the value of all the increments, okay? So this is okay. So I have perhaps okay, the indicator that x0 is equal to 0. Okay, and then I have the event that for all j in 0 and -1. And then I want xi j to belong to some interval ij, okay, where ij, it's really ij x omega. And what's this ij? Well, this is equal to 0 omega I, omega j, if x j plus 1 minus xj is equal to 1. And this is omega j 1 if xj plus 1 minus xj is equal to -1. And this is the empty set in all other cases. Okay, these events, they are equal. Okay, I've taken this out, but I could have put them this here. Okay, and now, I mean, x and omega, they are fixed. So what you have, this is really the same thing as the product from j equals 0 to n minus 1, q xij in ij. And now, with our construction, well, this thing is nothing more than, well, x0 equals 0, and then you have q omega x0 x1, q omega xn minus 1 xn. Okay? This probability here is just that, just by construction. Okay, so okay, this ends up our construction. Now, what we want, okay, is a system and a transformation under which xn will be a function of all things, but we want xn to have the, okay, so now we want, okay, let me tell you what we want to do. So we want to find omega, okay, so this will be, okay, this is going to be a large product space. Such that xn with low p0 bar can be constructed as a functional. I think the answer comes from the second requirement that we want to have. Okay? Because the second requirement, okay, and then we want t from omega to omega, which is ergodic. And we want that uk, which is just tau k minus 1, we want this thing to be tau 1, tau k minus 1. Okay, because we want to apply the ergodic theorem. So we want that each. Okay, so in particular, you want to consider x under a law for which these increments, they have the same distribution. Okay, because if not, I mean, if this thing is measure preserving, this is what we will obtain. So what's important here is not a law under which these things are independent. It's really, the important thing is you want things to have the same distribution. Okay, you want to show that this sequence here is ergodic, which is, yeah, exactly the second interpretation of being ergodic. Like you can find a system and a functional. Okay, so yeah, I think it's safer to leave things here. Yeah, you can try to think about it. Basically, the large product space is nothing more than, well, you have the environment. Okay, T is going to act by shifting the environment, and then you have yeah, IID uniform random variables, but you want to have sufficiently many of them and a shift operator on them, which is such that this is true. Okay, so you can try to imagine that. Yeah, I didn't do that. I looked at the solution right away, so I cannot tell you whether it's difficult or not. But I'm sure it's very satisfying if you find it by yourself, so you can think about it. Do you have any question? Okay, so I'll see you on Friday, and we will complete this part.